Hey everybody, welcome to today's webinar session. This is Troy, who is a Customer Success Manager from MIDAS IT HQ in South Korea. And thanks for joining expert webinar session today. And today's session will be conducted by Mr. Ong from company name Dr.Toh in Malaysia. I can say that he is expert to use GTS NX and carrying out 3D analysis. And I think that this Dr.Toh is an unrivaled company to design the geotechnical project with the 3D analysis. So please focus on his presentation and get useful knowledge for your upcoming geotechnical project.
Okay. First of all, I want to thank MIDAS IT for inviting us to share our experience in using the software. We have been using the software since 2010. We produce about 10 to 20 models every year using the software. And it helped us to understand the soil mechanics and also help us in decision making. So the focus today is how to model piles in MIDAS GTS NX. I will give a very short introductions on the company that I work for. Then I will introduce a new method to estimate the pile bearing capacity and the corresponding settlement up to ultimate load. That is the key. Then I will present 3 working examples. One is the installation effect of span pile at the Riverbank. Next is the large movement of the bridge abutment, which supported by pile. And the last example will be the effect of multi-excavations next to the underground MRT stations. I will demonstrate all the working files at the end of these presentations. We are a geotechnical consultant based in Kuala Lumpur, Malaysia. We undertake all geotechnical design and analysis. And we also offer litigations advice and as an expert witness in the court. You may want to visit our company website for more information. Let's go into the topic today. We can model piles in MIDAS GTS NX using solid element, embedded piles or beam element, with or without interface. You might want to master all the 3 methods because you may not know when you need to use it in your modeling. Although the solid element is not very efficient in numerical modeling, but it is very useful in modeling the special situations where, say, you might want to model a low friction at certain portion of your pile due to whatever reason, for example, a cavity problems or that piles already collapsed. Embedded piles is useful when you have a large pile group, for instance, pile supported embankment, or stabilizing your slope with piles. The problems with the embedded piles is that you cannot define interface for the embedded pile. The most rigorous and efficient way to model the pile is by using the beam element with or without interface. I have 2 examples to show you here. These are single pile problems modeled using MIDAS GTS NX. One is a long pile problems, and the other one is a short pile problems. They all socketed into the rock. Now, if you model the pile with interface, beam with interface using the highly nonlinear TZ model, you are able to produce the load settlement curve with very high, very non-linear linearity, right? Like as shown is as a red color line here. Now, if you don't model the PAL interface, the PAL response will be linear elastic. Okay. Another parameters for the PAL interface is a normal stiffness modulus, Kn. The Kn is the spring constant for the PAL in the normal directions to the soils. The lateral PAL response is sensitive to the Kn value. If you input a low Kn value, the PAL response will be softer than what it should be. And if you use a very high Kn value, you will have a numerical instability problem. So we have developed a range of Kn value for use by back analyzing laterally loaded PAL in clay and sand, so that the lateral PAL response is purely dependent on the soil in front of the PAL and not influenced by the interface. You can find the information in this paper. Now, can we model PALs in 2D constraint model? The short answer is no. Because you are not able to model soil flows in between the PALs, and you will overestimate the axial load, you will underestimate the bending moment. The magnitude may be out by 30 to 50%. We found that some embedded PAL show short PAL behavior, that is less bending moment. The PAL is very rigid, and we express this problem in this paper. Now, I'm going to introduce a new TZ and QW curve. I will explain what is new and whether it's worth for you to explore it. We have developed a new TZ and QW curve from 100 instrumented test PAL. All of them are both PALs. The model can simulate hardening and softening for the TZ curve, and hardening and the stiffening QW curve. The initial stiffness of the TZ and the QW model is a function of SPTN value, and the model was heavily tested. The advantages of these models are, first, the TZ and QW curve are correlated to single parameter only, that is SPTN value. In other words, you can estimate the bearing capacity and the settlement once the SPTN value is known. Second, this is a unified design model for PALs in soils and PALs in rock. The QU for geomaterial ranges from 0.01 MPa to 100 MPa. Number three, we define the upper bound and lower bound line for shaft and base resistance and the shear modulus. This is very useful for engineers to evaluate and make judgments on their PAL results. Number four, the best thing about this method is that you can calibrate the parameters for this model using the data from your instrumented test PAL. You can find the details in our paper published in Geotechnical Engineering, ICE, UK. Chai equations, which was originally used to model the stress-strain behavior of the concrete, was adapted to model the softening TZ curve. The input parameters are ultimate shaft resistance and the corresponding shaft displacement. KIS is the initial stiffness of the TZ curve, which is a function of shear modulus of the surrounding source, and a constant R, which control the degree of softening. The Rambert-Osgood equation, which was used to model the stress-strain behavior of the alloy, was adapted to model the hardening TZ curve. The input parameters are ultimate shaft resistance, the KIS, constant alpha and constant R. Constant R controls the stiffness before the peak, and the shaft displacement can be modeled by adjusting the constant alpha. Using the same equations, I mean the Rambert-Osgood equations, we can model the hardening and stiffening QW curve by just changing the constant T. We back calculate the shear modulus of the soil surrounding piles from about 500 DZ curve and plot against the SPTN value. And the correlation is shown in this figure. The trend is increasing shear modulus with QU in log Q. Performance of the model. We compare the predicted pile top settlement against the measured pile top settlement at twice working load or at maximum test load for 35 piles in our database and 27 piles around the globe. The result shows that the model can predict the pile settlement to an accuracy of maximum plus minus 3 to 5 mm deviation. For most of the pile, the settlement can be predicted accurately. Using the same model, we predicted the pile top settlement for 2 maintain load tests in Cambodia perfectly. The piles were 800 mm diameter board piles socketed into grade 3 sandstone. These are class A predictions where the predictions were made before the load test. That concludes the introductions of the new DZ and QW model. This is the first project applications. The objective of this analysis was to understand the mechanism of the slope movement due to installation of span pile at the riverbank. Before we go into the full 3D analysis for pile group problems and the slope, we did some verifications for single pile problem. This is a model for single pile in soft clay. The clay is modeled by modified chem clay model. The dimension of the mesh is 10 by 10 by 21 meter in depth. The water table is 7.5 meter below ground. The initial radius of the pile is 0.1 meter, and it will be expanded to 0.4 and 0.8 meter radius. This is the total displacement contour looks like after the expansion. And if you plot the vertical displacement of the model, you can see that the soil is actually heaved around the pile in a manner similar to as reported by massage. This model is very useful when you want to model the heave of the pile due to installations of another pile in soft clay. This is a graph of radial displacement plotted against the normalized pile radius, and this shows good agreement with the published data, where the radial displacement dissipate very quickly against the distance from the pile face. Similarly, the normalized excess port pressure dissipate very quickly against the distance from the pile face, and the response is comparable to the Randolph result. Now, we do the 3D analysis for the pile group problems at the riverbank. There are 16 piles for this pile group. The pile diameter is 800 mm diameter, close-ended. The piles were driven to set at about 60 meters. The distance from the pile to the crest of the slope is 9 meters. The slope is 21 degrees in gradient. The water table is 7.5 meters below ground. And the SPTN value for the top 60 meters is 0 to 4, which imply very soft clay material. The parameters were developed from 1D console tests, and they are listed here. Below the soft clay is loose sand. The behavior of the sand is modeled by more column model. We only model the top 21 meter where the soft and loose material are, because they have prominent effect to the slope movement. We use laptop for mobility reasons. This is the configurations of my laptop. The CPU is i7 9750, 64 gig RAM and Quadro graphic card. The computational time for this model is about 2 days. The average time required to install one span pile is about 1 day. The construction sequence is shown in the figure below, following the designated arrow, like this, from pile number 8 to 14, to pile number 10, to 9, 5, 16, 13, 1, 8, 4, 15, 12, and so forth. Generally, it can be simplified as installing pile at row number 1, followed by row number 2 and row number 3. The model construction sequence are: first, generate initial ground stress. Remember to deactivate the K0 condition because this is a slope. The second step is to deactivate the pile row number 1 and apply the radial displacement. There are 3 piles in the first row, so the construction time is 3 days. The third step is deactivate the pile row number 2 and apply radial displacement. And at the same time, pile number 1, row number 1 is activated, and the material is changed to concrete from the soil. The constructions for this step is 5 days because there are 5 piles in this row. The second steps and the third step are repeated for the rest of the piles. This is the lateral displacement plotted against the distance at the ground level. The result shows that the slope will move about 350 mm. This is the excess pore pressure plotted against the distance at 7.5 meter below ground. The maximum excess pore pressure was observed in the soil behind the row number 3. Low excess pore pressure was observed in the soil in front of the pile. This is because the excess pore pressure is able to be dissipated through the slope face. This is the measured lateral deflection at the pile head towards the river. The thin line are the measured lateral movement of the pile top for pile row number 1, and this group are the movement for pile group number 2. This is the outer pile. This is the inner pile. There are 2 parts of the lateral movement. The first part is due to the installation of the span pile, and the second part of the movement is caused by the consolidation of the induced pore water pressure. And this is our predictions for pile row number 1, and this is our predictions for pile row number 2. What I can say is that this prediction is quite encouraging. With that, I conclude the first working example. This is the second example. It is about the lateral movement of a bridge abutment. Our client notified quite a number of parallel cracks on the pier in front of the bridge abutment, and the gap between the bridge beam and the pier was opening, right? They want us to investigate the cause of the cracks. This model includes a bridge abutment and reinforced soil wall which was founded on piles in soft clay. There are groups of span piles, two board piles, grid beams with anchors, and below the embankment is soft clay. The soft clay was treated by PVD. This is the mechanism of the movement. Diagram number 1 is the configurations of the wall as per design. The gap is 330 mm between the top of the wing wall and the bridge beam. The wall has undergone some translational lateral movement in the soft clay to the left due to the construction of the embankment, which is about 50 meters away. And therefore, the gap is closed. Further movement of the wall has caused the pier to rotate at the point of rotation and caused the gap to reopen. At the same time, tension crack will form on the outer face of the pier when the bending moment was exceeded. So this is the mechanism. I will show you how we model this in MIDAS GTS NX. This is the configurations. There are two abutments for the bridge. They are symmetrical. Both of them have shown some degree of distress. The bridge approach was made up by a reinforced soil wall supported by 300 mm diameter span pile. The span pile are 21 meter long, driven to set, and spaced at 1.7 meter centers. The reinforced soil wall is about 11 meters, tapering down to 9 meter, butting to the earth embankment here. The earth embankment was reinforced with high strength geotextile, and below the embankment, they are PVD. The extent of the reinforced soil wall is 50 meters. The soft clay is about 10 meters thick. The undrained shear strength of the soft clay is about 10 kPa and increased with depth to 20 kPa. Below the soft clay is firm clay and followed by residual soils. The soft clay was modeled by using the chem clay model, and the residual soils was modeled by using modified more column model. It is very important to compare your undrained shear strength of your model with the measured undrained shear strength when you use chem clay model, such as shown in this figure. We compare the undrained shear strength from the chem clay model and the undrained shear strength from the CRU test and as well as the CPT test, so that you know what is the undrained shear strength you are modeling when you use chem clay model, because you don't input undrained shear strength in chem clay model. To find out the cause of the distress, we simulated closely the construction of the bridge abutment. To reduce the computational time, we only model half of the problems, okay, the symmetrical plane. This slide shows all the structural elements for these problems. This is reinforced soil wall. These are the span piles supporting the reinforced soil wall. In front of the span pile, there are board piles. The diameter for the board piles are 1.5 meter and 40 meter length. There are anchors behind the grid beams, and this is embankment. Below the embankments, there are PVD, and the grid beams and the geotextile are embedded in the embankment. Now I'll explain the construction stage. The first step is to generate the ground stress. The ground level is RL 1.4 initially. Then put a minimum fill for working platform. Then install PVD and lay geotextile below the embankment. Then increase the height of the embankment gradually to RL 5.3 and consolidate the ground with 6-month period. Then construct the bore piles, pile cap, and the span pile below the reinforced soil wall, and construct gradually the reinforced soil wall to RL 5.3. After that, remove partially the embankment down to RL 2.3 to install the span pile at this portion, grid beams and anchors here, and backfill the embankment to RL 5.3. Then construct the reinforced soil wall and embankment gradually to RL 11.4. This is a total displacement at the end of the constructions. The result shows that the field placement behind the grid beam resulted in significant settlement and lateral movement, and subsequently pushed the reinforced soil wall and pile deck forward and caused a crack at the pier. This is the lateral displacement of the pier at the abutment. The measurement was only taken in January 2017 when the distress was first observed. Although some movement had already taken place before January 2017, but our model was able to capture the lateral displacement of the pier for the same period of time. This is our simulations. This is the measurement. Similarly, our model was able to match the lateral displacement of the slab at abutment for the same period of time. This is our simulations. These are the measurement. Our model also able to match the consolidation settlement versus time below the embankment. Now, this is the plot of the lateral displacement plotted against the settlement below the embankment for various KVE. KVE is the equivalent permeability of the clay improved with PBD. There are two parts of the movement. One is the initial stage. I call it stage number 1, where the lateral movement is small. And second stage, where the increment of the lateral movement is close to the settlement. You can see that the lateral displacement accelerate when embankment is filled to higher than RL 5.3. And with that, I conclude the second example. This is a third example. Our client was desirous to redevelop an existing shopping complex. The redevelopment is located within the second reserve of an MRT station, underground MRT stations. According to the local railway act, the basement has to be designed in such a way that it will not cause excessive movement to the MRT structures. The maximum permissible induced movement of the MRT structure is only 15 mm. This model includes 4 deep excavations, 2 tunnels, 4 nearby buildings, and many piles, which was used to support slabs and for temporary structures. This is the layout plan of the basement excavations. This is the existing 2-level basement. The new 3-level basement will be constructed parallel to the existing 2-level basement. The new basement wall is butted to the underground MRT stations by a series of buttresses. The surrounding structures are twin tunnels, 4-story sublots here and here, 5-level underground MRT structures and vent shaft, hotels and offices here, and 2 basement car park at the bottom. I will show you in a clearer picture in the next slide. Okay, this is the size. The size of the mesh is 200 meters by 250 meters by 79.5 meter in depth. This model includes, as I mentioned, the old basement wall and the new basement wall within the old basement wall, 2 tunnels, surrounding structures and temporary structures, the branching columns. This is a fully coupled effective stress analysis. We model the ground water flow for every construction stage. The property of the unsaturated soils is essential for transient flow analysis. Interface with low permeability with K value of 1 to the power of -10 meter per second was modeled for the walls. We model the surrounding buildings with equivalent slab follow the parallel axis theorem by Timoshenko, that we can output the strain and compare against the Berlin charts that I'll show later. We model the twin tunnels by imposing the prescribed displacement to form an oval shape, follow the Logarithm and Polos methods. We use hardening soil model to model the residual soils. This is a very established correlations for the E50 that we use in Malaysia. The computational time for this model is about 4 hours. This is a plot of SPTN value for all the boreholes. We adopted the lower bound value for analysis. The ST plot suggested that the shear strength of the residual soil is 27.5 degree in friction angle and 9.5 kPa in cohesion. The water table is 0.5 below ground. Now I'll explain the construction stage. We start simulating the construction of the pre-war buildings, 4-story buildings, back in 1940s to get the ground stress correct. Then consolidate the ground for 30 years. And this will bring us to 1970s. We then simulate the open excavations for 2 basement for 2 level basement that has a shared wall with this redevelopment. This is a bottom-up construction. We then simulate the existing 2 basement excavations using the top-down construction methods and consolidate the ground for 37 years. And this will bring us to 2014 before the construction of the tunnels. We then simulate the construction of the tunnels and the 5 levels underground MRT stations and the vent shaft by sequential top-down constructions and reset the total displacement to 0. And this will bring us to 2017. We then backfill the old basement, the 2 level basement. We then consolidate the ground for 5 years, and then construct the inner walls for the new basement and buttresses butting the MRT substation. And finally, we simulate the top-down constructions for the new basement. This is the deflections of the diaphragm wall for MRT diaphragm for the MRT sub basement near the redevelopment site. This is the deflection of the diaphragm wall at the opposite side. This is the measured deflections from the inclinometer. And the lines with markers are the deflections from our simulations. And I will say that the predictions of the deflections is not too bad. I mean, the response is there, the magnitude is not too bad. This is a total displacement of the model at the end of simulation. The maximum deformation of the MRT structures is less than 15 mm. With that complies the local railway act. From the analysis, you can output the strain of the equivalent slabs, and you also can calculate the deflection ratio. And from Berlin charts, you can predict the distortion that will happen to the building. And this is the result. The category of damage is very minor. The category is 0 and 2. Category 0 means the building will suffer negligible hairline cracks of less than about 0.1 mm wide. And category 2 implies slight cracks with which produce cracks up to 5 mm. With this, I come to the conclusions. After that, I will go into the I will demonstrate the finite element model, and I will answer some questions. Okay. I have introduced a new DZ and QW model, which can predict the load settlement curve up to ultimate load with high accuracy. And the point is, it can be implemented in MIDAS GTS NX. I have presented 3 examples of project applications using MIDAS GTS NX. One is the insolation effect of the span pile at the riverbank, and the other one is the large movement of the bridge abutment, and the last example is the multiple structure interaction problem. I must mention that it is not our intention to build a complex model. We try to build the model as simple as possible. We always carry out 2D analysis before 3D analysis to get some idea of the problems, but sometimes the problems we face is in 3D in nature. For example, the flow of soil between piles. We need to construct such a big model to consider the interaction effect. So this ends my presentation slides. So I will go to the model. This is a model for power group analysis that we did for our client in Cambodia. The engineers would like to know what is the settlement for the power group. There are about 500 bore piles in this model, and there are 4 layers of soils. The top part are residual soils, and the third and the fourth layers, and the third and the fourth layers. Yes.
We can't see your models. Can you shift the screen?
Sorry. Okay, can you see the model?
Yes, thanks.
Okay, sorry. Okay, I start over again. This is a power group analysis that we did for our client in Cambodia. This is actually basically a power group analysis using the new DZ and the QW model. All right. I just want to show you the important features of this model. I deactivate the soils, and these are the piles. A lot of piles, different size and different length. All right. And we model a non-linear DZ curve for the piles. And we also model the stiffening QW curve for the piles. Those nonlinear TZ and QW curve were derived from the instrumented test pile. And then we can apply the load on the piles. And I just want to show you the results. This is the total displacement of the pile groups. The maximum deflection, the maximum settlement of the pile group is about 33 mm. And this settlement profile is very useful for structural engineers for them to design the reinforcement for the slabs. There is a finite element model for power grid problems. Then I will go to the model for the first project applications. That is the installation effect of the span pile at the riverbank. This is the model. There are two layers of the soil. This is soft clay, this is loose sand. And how we model the pile installation is by applying the radial displacement around the piles from radius of 0.1 to radius of 0.412. How we get the 0.412 is by calculating the equivalent area for 0.4 meter radius span pile. All right, so we apply the radial displacement for the whole length of the pile. Maybe I deactivate. You can see for the whole length of the pile. All right. Now I will show you the model for second project applications. That is the large movement of the reinforced soil wall due to the field placement of the embankment. This is the reinforced soil wall. This is the embankment, and the soft clay is below the walls and the embankment. I think I will just show you the important features. Let me hide the All right. So in this model, we actually model all the construction stage, and you can see here there are a lot of piles, span piles with different length. All right, and these are two board piles in front of the reinforced soil walls. These are the reinforced soil wall facing, and this is the grid beams designed by the local engineers. We just aim to find out the root cause of the large movement. Behind the grid beams, there are anchors. You can model the free length and the fixed length. All right. And the very important point I want to stress is that you have to make sure the pile is connected to the slab so that the load can be transferred from the reinforced soil wall to the piles. We didn't model the reinforcement for the reinforced soil wall. How we model the reinforced soil wall was just assign a cohesion of 100 kPa to model the reinforcement. We simplified the modeling of the reinforced soil wall because the reinforced soil wall is just acting as a counterweight. We have no interest to know the information, the deformations of the reinforced soil wall. So we just assign the high cohesion for the reinforced soil wall. All right. And I also want to show you how we model the PVD treated clay. So let me activate all the models. We use the method by Chai and Bergados, where we calculate the equivalent permeability for the PVD treated clay. In general, in short, the method is just to assign a higher permeability for the clay. For instance, we assign a permeability of 6 times of the original soft clay to the PVD treated clay below the embankment to simulate the treatment of the PVD. Next, I will go to the the big model, that is multiple excavations, twin tunnels, and the various low-rise buildings surrounding the basement excavations. The highlight of this analysis is that we simulate the problems by using the fully coupled effective stress analysis. All right, fully coupled effective stress analysis. So for every excavations, we define the water pore pressure boundary for every excavations, and also for every construction stage, we have to define the time steps. I want to show you how we model the tunnels for this model. All right, yeah. We model the our practice in a company is we try to model the construction of the tunnel by the method follow the Moller's method, which we simulate the tunnel, the excavations of the tunnels by applying the grout pressures, phase pressures, and slurry pressures. Basically is a very detailed simulations of tunnel constructions. But in this case, the model is very complex, and the number of elements already reached to the maximum level we can handle. So in this model, we use a simplified method, follow the Colos and Loganathan method. The basic idea is just to model the tunnels by imposing an overshape of the tunnels. This method is better than contraction methods because the results and deformations from Polos and Loganathan method is closer to what we observe at site. By using the contraction method in the tunnel modeling is actually meaningless because you prescribe the contractions, and the forces in the tunnel is dependent on how much you compress, how much contraction you apply on the tunnels. All right, and we model the low permeability for all our walls to simulate the wall. The last thing I want to show you for this model is the result. It's a huge model. So I want to show you the pore pressure for this model. All right. We simulate the drawdown of the water table for every excavation phase. We define the unsaturated soils properties for the residual soils. I just want to show you the variations of the water table in our simulations. It will be like this. So MIDAS GTS is able to simulate variations of water table because due to the excavations very well. All right. The last thing I want to show is this one. You have to define the soil water characteristic curve for the your soils. You can estimate the properties using various type of functions. This is very important and essential for you to model the realistic, very high nonlinear drawdown in the soils. All right. The last model I want to show you is you have to check your model to prevent any free face in your model, such as like this, the free face in the 3D model. All right, this is very important. The problem with MIDAS GTS is that MIDAS GTS NX still allow you to continue with the analysis until it complete. But the result you get from this analysis is wrong, because the load cannot be transferred from one point to the other, because if you have free face, the load cannot be transferred. All right, so you have to avoid this. This is the one example that we totally discarded the results because of this small free face we face, and we have to remesh the whole thing and redevelop the whole model. So I just want to show you all our models are free face free. I mean, there are no free face in our models. Let me deactivate the pause. You can see that is your responsibility as an engineers to make sure your model is has no error. All right, and I also want to show you this model is perfectly all right. There's no free face in this model. So let us check the this model. It takes some time to load. Okay, so there's no free face in this model. So this model is perfectly all right. And why don't we check this model as well? So you can see there is no free face in this model. So this model is fine. So with that, I complete my demonstrations for the finite element model. Now I will look at the questions, whether I can answer some of the questions. There's a question from Mazen. He says that it might be better to present only one project and explain it in more details. We try to do it, but we feel that this is just to expose you to the problems, and it is just to a platform to show what this software can do, and this will give you some guide to model. It's impossible for me to teach you the full steps in this such a short webinar, and you can contact me if you want to learn more about this. Okay. 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 There's a question from Lo Ying. She asked, for BB Plaza excavations, how did you define the water table levels within the excavations, MRT tunnels, neighboring basement? For fully coupled effective stress analysis, what is the reasonable tolerable error? As I mentioned and show you just now, we carry out the fully coupled effective stress analysis. It is the same method that you model your basement excavations with flows using the stress seepage analysis. The difference is just that in fully coupled effective stress analysis, you combine the seepage and the stress analysis into one, and you have to define the time steps for the excavations. How we model the water flow is by we fix the water table at the far end, around the boundaries, and we define the zero port pressure at the base of excavations, and let the programs to calculate the water table for you. Regarding the tolerable error, don't ever change the convergence criteria unless you know what is the consequences to your model. We have experienced in changing the convergence criteria, and it will give you a serious error if you try to reduce the convergence criteria. So I don't suggest you to change the convergence criteria. Okay. From the same person, Law, she asked for the power group model in Cambodia. I saw the load is not applied on shear wall, column, raft, or something like that on the power top. Is this simplifications just to understand the power group behavior when all powers are loaded to its working load? Please correct me if I'm wrong. Interpret your model, your methods of power load modeling. Yes, you're right. In this model, we can we didn't model the shear wall. We didn't model the bending moment on the what do you call that shear wall. We can do it, but this model is good enough for the structural engineers to design the reinforcement for the slabs. The point in modeling the power group settlement is that it is not how complex your model is that will give the good result. The point is whether you can model the load settlement behavior correctly. That is more important. I would recommend you to look into the method that we developed over the 5 years from our experience. That is more important. And this will give a general idea on how much the power group will settle. And the single pile behavior indeed is totally different from the pile group behavior. Single pile behavior, the load transfer to the base will have. The pile group, for the pile group behavior, the load will be transferred largely to the base, and the settlement is controlled by the soils or the rocks below the pile base. And we need to do this kind of analysis to understand what is the expected pile group settlement. You cannot tell the pile group settlement from single pile load tests. So this is the intentions.
All right, so thank you for your presentation, Mr. Ong. And I hope that you guys got useful knowledge from this expert webinar session. And company Dr.Toh is a quite good company for geotechnical design as you watch it. So please contact him and get more productivity in your upcoming project. Your queries will be sent out with the response through your registered email. Thank you very much.